Hello, it's Keith here, and this is lesson 73 of the platform-specific series of my Gameboy assembly programming tutorials. We're back on the Gameboy again, and we're back doing sound again. Why are we doing sound a second time? Well, we wrote a little sound driver before called ChibiSound, a simple beeps driver for old Atari Space Invaders type games, very simple sound effects. We're going to do something a little bit better today, and we're going to write a driver called ChibiSound Pro. The Pro moniker suggests it's slightly better, but Pro might be an exaggeration. It's supposed to be a parody of the Sound Blaster Pro, which wasn't all that good either. It was better than the original, but not as good as the Sound Blaster 16 that came after it. But anyway, we're going to do something a little bit better. We're going to be aiming for music now. Before we just did little bleeps. Now we're going to be doing simple music. So we're going to create a driver that can do multiple channels at the same time, a much wider range of volumes. We just had a 1-bit volume before. We now have an 8-bit volume. We're going to support up to 127 channels, still the same noise feature, and the pitch is now going to be 16-bit, whereas before it was 6 bits. We've got a wider range. We're also going to add a lookup table for the notes of the octave, which is going to allow us to do tone match sounds on different systems, hopefully. And I've written a little music player called Chibi Tracks and a little Windows music tracker called Chibi Tracker Pro. So we've now got a 3-part environment for creating music: Chibi Tracker Pro, Chibi Tracks the player, and also the ChibiSound Pro, which is the platform-specific driver. And I've written these for basically all of the systems in my Z80, 6502, and 68000 systems. And in theory, at least, I could write them for all of the other ones in the 8086 and the ARM and things as well, which is probably a good point to point out. If you want to support this content and see more made in the future, please consider backing me on Patreon, because I'm not going to spend my time writing this on the 6809, 8086 and ARM if no one wants it, because I've got other things to do and I can't write games on all those systems anyway, so I don't need multi-platform music on all those systems, do I? So anyway, what is the ChibiSound Pro going to do? Well, we're going to pass 4 parameters, 1 in H, 1 in L, and 2 in DE. So DE is a 16-bit value for the pitch, the volume, and the noise. And the channel. The noise is just 1 bit of the H register, the top bit, and the channel number is the rest. So in theory, 127 channels. But in practice, we are aiming for a minimum of 3. The reason for that is I create my music based on the AY sound chip. That's the original system. And so that had 3 sound channels. So I aim for at least 3. But I always write the code in a way that will support a value from 0 to 127, with the lower numbers being more important. So if we have to ditch a few, we ditch the higher numbers and prioritize the lower numbers. Now, how does the Gameboy sound work? Well, we did cover it before, but we'll go over it again. Now, on the Gameboy, we have 4 channels, but they don't all work the same. Channel 1 is a tone and sweep channel, and so this can play basic tones, and it can also do sweeping effects, although we won't actually be using them for this purpose. We don't use any of the kind of more advanced envelope functions for ChibiSound Pro. The second channel is a pure tone channel, so basically we're going to treat channels 1 and 2 as just tone channels. They're going to work for the same for us for today's purpose. Now, the problem comes with channels 3 and 4. Channel 3 is a wave channel, which means it can play 4-bit per sample, total of 32 sample wave samples, so digital samples. You're going to struggle to make it play a long speech sample. You could do it if you were clever with your timing, but it's not really designed for that, so not the ways maybe you'd be thinking of. Channel 4 is a noise channel. Now, channel 4 is really okay for noise, but the problem is ChibiSound Pro has a noise parameter for each of the channels. So each channel can be told to turn its noise on or off, and we only have 1 channel to do that. So what we're going to do is we're going to have virtual noise channels, and if we're asked to turn noise on for channel 1, we're going to remap that to channel 4, and then when we're asked to turn it off, we're going to remap the off command to channel 4. So we're going to have to do that in our code. With regards to our third tone channel, because we want at least 3 tone channels ideally for the sound, for the music software to work ideally, what we're going to do is we're going to use channel 3, and we're going to give it basically a pulse wave, and we're then going to use that as a third tone channel. And the volume isn't quite the same the way it works, and I don't think it quite matches, but it's as close as we can get, and it's not far off. So that's what we're basically going to do. Okay, so let's go over to our source code and let's see and hear what we're going to be doing. So let's get the oscilloscope up so we can see it, and let's play with our little test programs. So we've got 2. The first one is the ChibiSound Pro test. This is designed for actually testing that the driver is working and for configuring the tones. You can hear we've got a rather nasty squeal here, and if I use the joystick here, the virtual joystick, I can change the number, and you can hear that the pitch gets lower as the number gets lower. Now, if I press the fire button, you can hear the noise effect is enabled. So you can tell basically that we've got a less varied range of noises than we have of tones, but it's actually pretty good on this system. Some systems are quite limited, and this one isn't so bad. So that's the test routine. Now, what we also have though is the Chibi Tracks test route. Now this one's far more impressive. This one's going to play a music file. Now this is, it's playing a little bit slow because it's not interrupt driven, but this is the music for the Chibi Akamas theme. This was originally written in Arcus Tracker. I converted it to the Chibi Tracker Pro and then exported it as a binary for the 10K Sub Special. It's that same binary playing today, and this is the important thing about Chibi Tracks. It's not just a tracker that can export to multiple destination systems. It's actually a music player that can play the same binary file on all of the destination systems. So there's no re-exporting, and also it works with different destination memory addresses. You don't have to compile the destination memory address in. You can, but there is a relocation option, and it's not, doesn't use that much extra memory. So the idea is that you can export your file once for the Amstrad CPC and use the same file for the Spectrum, the Game Boy, the NES, the X68000, the Genesis, whatever you want, even though they're completely different systems. It's a theory anyway. So anyway, that's a quick demo of it in action. What we're going to look at today is the Game Boy sound driver. Let's get rid of that oscilloscope, we don't want to see that anymore. So the first thing we're going to have a quick look at is the octave. Now basically this is a lookup table of the values for the DE pair that are going to be the pitch we want. So we pass a pitch in DE, and we've got the ones for the notes here. You'll see you've got EF, A, B, C, D here. Now if you wanted a sharp or flat, all you basically do is you take two of the values together, add them together and divide by 2, because the sharps and flats are directly in between the pure tones. So that's what we've got there. Now what we do have is this line here can be disabled by the SMS transpose function, and that is basically used for systems like the Sega Master System, where the very low frequencies aren't accurately representable. So I've got a set of values there, but they aren't tone matched because I couldn't get them to match on this system. Maybe it's possible, but my I use a frequency analyzer to work out what notes they are, and it wasn't able to detect what they were. So if it's possible, it was beyond me. And so anyway, basically, if you disable these, it will shift the tones up an octave, which is what I did for the playback there, and that will make the notes correct, but the pitch will be higher than the original song was created for. So it's a bit of a trade-off. Now, basically, the rest of the code is going to handle the requests to change the sound. We've got a few bytes of RAM here that are used to remember the noise state, because as I said before, we're going to simulate 3 channels that are able to actually play the tones and in theory play the noise, but when the noise is turned on, we're actually going to redirect that to channel 4. Now, at the start of using this, we need to run the initialization routine, and what this does first is it clears all of the registers. The memory mapped registers start at FF10 and they carry on basically until FF26. After that, we've got the wave pattern RAM, which we will also set up. But the first thing we're doing here is we are setting all of those registers to 0. So we're starting from a constant state, and we don't have to worry about anything weird being in there from when the system started up. The next thing we're going to do is we're going to turn the left and right channels on. We're going to turn all of the channels on here. So we're loading that value there for on, and we're writing that to FF24 and FF25. So that is going to set the sound channels and the selection. So we're enabling stereo and setting them to the maximum volume there. The other thing we're going to do here is we're going to generally turn the sound on, and we do that with bit 7 here of FF26. So we're writing a bit 1 there for the enable there. Now when it comes to actually turning the individual channels on, we will do that for the channels themselves later on, but this is just getting things set up so everything works in general. The next thing we're going to do is we're going to write our wave. It's kind of a pulse wave. So the way it basically works is the memory address is FF30 to FF3F. We'll take 2 1 nibble samples that make up 32 in total. So there's 16 bytes, 2 samples per byte, 32 samples. And so what we've got here there is 16 bytes here, and we're writing the values 0 from A and 255 from B. And you can see here we're writing mostly A's followed by 1B there. So we've got 7 empty samples and then 1 255 sample, and then 7 empty samples and then 1 255 sample, which makes a reasonably comparable wave sound that sounds similar enough to the tone channels. So that's how we are simulating a third tone channel, if you will. Now all of the actual functions happen with the ChibiSound Pro set, and this is what we want to call when we want to change the thing that the sound channel is playing. So basically what we do is we pass this with H as the volume from 0 to 255, 0 being silent, L being the channel number with the top bit being the noise state, and DE being the pitch with the 0 being the lowest pitch. So the first thing we're going to do here is we're going to decide what channel we're going to use. So basically we're going to load BC with the first value there, and we're going to see if we are using channel 0, if our L register has been passed to 0 in the bottom 2 bits. If it has, we're going to use that value. If not, we're going to change it to FF17, and we're going to see if we've got a value 1. And if we have, we're going to use channel 2. If not, if it's a 2 or a 3, we're going to use the wave channels. So we're loading the C part with 1C. So we're pointing at FF1C, which is the volume. Now the volume on the wave channel is very different to the other ones. Now it uses a 2-bit value, whereas the other ones use a 4-bit value. But the value is actually functionally different. For most channels, the volume will be a higher number for a higher volume. So a value of 15 in the V bits will be the maximum volume. A value of 0 will be the lowest volume. On the wave channel, it's a bit odd. Those 2 bits there, a value of 0 will be off, a value of 1 will be full volume, a value of 2 will be 50%, and a value of 3 will be 25%. So it's a little bit backwards, really, in some ways. It's almost not even backwards, because 0 is the lowest volume, 1 is the highest, and 2 and 3 are in between. Anyway, so what we're going to basically do here is we are going to sort of correct for that. So what we're going to do here is we're going to take, if we're using the wave channel, we're going to take the top 2 bits, shift them to the right, flip them, and then we're going to add 1. And so this will effectively basically set our volumes to the right kind of values for that register there. So we're setting those 2 bits there for our volume. And then basically what we're going to do then is we're going to skip down to our volume setting routine. But if we're not actually setting the volume of channel 3, then what we're doing is we're just simply masking the top 4 bits here instead. Now what we're going to do next is we're going to check if we are setting the noise, if the noise is to be set, and we're checking the top bit of L there to see if we are making a noise. If we are not making a noise, then we're going to load that volume value into the register that was specified by BC here. Now BC will be pointing to the volume part of the register here, so we are pointing to one of these values here, and so that will load the volume in for the correct channel. Now the next thing we're going to do is we're going to set the frequency. So basically, how do we set the frequency? Well, we need to set the H and L part for our channel. Now actually this is basically the same for channels 1, 2 and 3, so even the wave channel has basically the same settings here. And so what we're doing here is we are basically just converting our 16-bit value into a 11-bit value here. So we're just shifting the bits into this kind of position here by sequential bit shifts. We're then loading in the low byte there, and then the top 3 bits for the high part, and we need to set the top bit to 1 there to enable the channel. So that's what we're doing there, and we're writing that to the following registers after the volume. So we set the volume first, and then we set the L and H, and that is the same. Even though the first volume was different for channels 1, 2 and 3, it's actually the same for these. Now at this point what we're going to do is we're going to run this routine called get channel noise state. Now this will check the flag for the channel before, because we're making a tone at the moment, but this channel might have had its noise state set before, and in that case we need to turn off channel 4. So what we're doing here is we're running this subroutine here, and what this is doing is this is basically calculating the offset in the channel noise table, which is in memory here, and it's calculating the offset for the current channel into BC and returning. And then what we're doing here is we're checking if the state was previously off. In that case it's still off, so we can just return, but if it was on before, then what we need to do is we need to silence that noise by writing a 0 to FF21. FF21 is the volume for the noise, so that's what we're doing there, with silencing that noise there. Now if we were making a noise, we were testing that at this point, and we were jumping to this noise routine here. So that's what we've got here, and what this is basically going to do is it's going to mute the tone channel. So we're writing a 0 to the volume of the channel that was previously selected. So we were selecting our channel up here, our volume channel up here, and this will mute either the wave channel or the tone channel accordingly by writing a 0 to that. And then what we're doing is we are calculating the volume for the noise channel, and we're writing it directly to FF21, which is the volume for the noise channel in the same format as the first 2 tone channels. And then what we're going to do is we are going to calculate the frequency, and actually all we're doing is we're taking the top 3 bits of D and we're shifting those to the right by 1 and XORing the bits in there. Now that is so that we get the correct value for FF22. Now FF22 is the what's known as a polynomial counter. So we're basically setting 3 of the S bits there, and we're setting the D bits there. Now the D bits are the dividing ratio, and the S bits are the shift clock frequencies. So we're not actually using them all, but it was to make a good range of values. We wanted a sort of nice middle range of values. We didn't want static that no one would be able to hear. We wanted stuff that was reasonably within a nice range for sound effects. So that's why we aren't using all of the bits there of our D register. And then finally what we're doing here is we are setting the noise flag to 1. We're writing a 1 to BC there, and that's so that next time when this channel later has its noise disabled, we know that that's happened and we can turn the noise back off. So that's what we're doing, and that's really all there is to it, I suppose. I mean, as I say, we're using most of the functionality. We're not using the sweep functionality, and obviously there's some more complexity, but with this ChibiSound Pro, and with regards to basically everything I do in my tutorials, it's always about trying to make something that's reasonably functional, but it's very portable and reasonably easy to port. You know, I want things that do the same job or a similar job on all of the systems, and that don't, you know, drive me to insanity in the process, and can be debugged easily and ported to other systems later. And so, as I say, like everything I do, this isn't going to be the best example. It's not the best music player. It was never intended to be. It was intended to be a simple music player and driver that if I wake up one day and decide, oh, I'm going to program the Power PC today, and I want to write a music program for it, I can hopefully port this to that as well. And you know, that maybe will happen one day. Anyway, I hope you've enjoyed what you've seen. Thanks for watching, and goodbye.